Welcome to the Artificial Intelligence Podcast with your host, Dr. Tony Huang. Today I'm with a special guest. Pavle, can you introduce yourself?
My name is Pavle. I'm the founder and CEO of Aether.
Cool. So, what was your journey like to become the CEO of your own company?
That started a long time ago. The company was started out of work from undergrad. It's been a few years since then, putting together the technology. And from then, figuring out not just how to get the technology to work, but how to turn it into a product and how to find customers for that product. Deep tech is never necessarily easy or straightforward, and we have a lot of complexity in what we do, but things are working and things are really taking off right now.
That's cool. You guys do like material science work, is that correct?
I would describe our technology as taking proteins that exist in nature that do everything from break down the food that you eat to build your body atom by atom, and figuring out how to engineer those proteins to rearrange atoms in any way that we want. And then finding applications for those new classes of protein-based nanomachines. The two main types of applications we've found that are working well from a go-to-market perspective are applications in the mining space, where we have developed a new class of basically proteins that allow us to extract metals with really high efficiency and a very low cost, and proteins that create new types of materials that haven't existed before. In both of these cases, the applications are things where we're enabling new types of value props and new types of products that haven't really been possible before. And the end-to-end process of Aether, if you want to think about this in your head, is we start with saying, what is a rearrangement of atoms that isn't really possible today, that if we could make it possible, would solve a really valuable problem? So some kind of chemical reaction, to put it another way. We then use our artificial intelligence and a robotic laboratory to iteratively design these new protein machines until we can actually make that atomic rearrangement happen. Once we have that machine that actually does what we want, we then actually build a full end-to-end product. And on the mineral side, we're building shipping container size pilot facilities that extract metals from the ground. On the material side, we have an entire lab here that's full of 3D printers and a bunch of different extruders, and just trying to see, can we actually turn this into a real product where we can then ship to a customer, not just get paid for it, but get feedback from them on what they're interested in. So it's really the end-to-end process from, here's an idea, wouldn't it be great if atoms could be rearranged this way, to we can do it, to how do we actually turn this into a product?
Like, what was the industry like before this? Were they doing it like, I don't know, were they using like organic chemistry to
Mm-hmm.
create these types of arrangements, or what was the technique that was like very common before this?
Yeah, the way we do this today is always using some kind of synthetic chemistry, right? Biology is very rarely used in manufacturing, and we can talk about why that is. But I think when you think about the way the human beings have built molecular products for centuries now, it's always been through synthetic chemistry for the most part, except for obviously things like beer, which we ferment. And the problem with synthetic chemistry, fundamentally, is not that it has to always be environmentally unfriendly. The problem is that it's a process that relies on brute force. And let me describe it in the simplest metaphor that I can. The way we try to drive chemical reactions forward using traditional approaches is by increasing the probability that certain atoms will form or break a bond at a time. And most of the ways we do that is a very brute force approach where you increase the temperature, or you massively increase the acidity, or you decrease the acidity. But you're doing things where, because you can't individually grab these atoms and force them to come together the way you want, you have to shake them together using different approaches until they just, on average, make the bond that you're interested in, or do whatever it is you want at the nano scale. And you could think of it as, if you buy a Lego kit, assembling the Lego kit by just shaking the box until everything's properly assembled. Is that theoretically possible? Yes. Is that going to happen in a reasonable amount of time? No. And so it really gives you a sense of the scale of the inefficiency of a lot of these processes, where we're talking about trillions of shaking actions at a time when we heat up huge reactors or something like that, because that's what we're trying to do. The advantage of this approach, and the reason why this is really a step change in the way to manufacture molecules, is these protein-based machines, they are not randomly driven. They are grabbing individual molecules, individual atoms, and they're forcing them to come together in a very mechanically driven way, exactly the way we want them to. And what's unique about Aether's approach in particular is we focus on engineering new classes of atomic rearrangements or chemical reactions, however you want to call it, whatever it's easier for you to think about it. It's very common for people to try to find proteins that already exist in nature that might solve the problem that you're trying to solve. As a company, we're not satisfied with that limitation. We don't want to bet that nature already evolved a protein somewhere that does what we need it to do, does what the human race needs it to do. That just feels like a very unlikely situation most of the time. So what we've gotten very good at is engineering proteins to execute these new functionalities, even if they've never been seen before in nature or anywhere else. And what that really allows us to do is when we think about the go-to-market strategy and the motions that we have to execute, it allows us to take a step back and say, if we just ignore the words synthetic biology or synthetic chemistry or anything like that, if we just ignore all those labels for a second, and we just think to ourselves, what is a new chemistry? What is a new rearrangement of atoms that if we could just do this, it would just open up so many new possibilities in terms of new classes of products, and then go for that new class of chemistry, new arrangement atom, and then build products from there. A good example is our metal binding program. We're getting really good at finding ways to extract just about any metal we want at this point from a variety of different sources. And it's really driven by this idea of, can we build the thought that was the genesis of that product line was, if we can design little machines made from proteins that can make or break bonds, can we design machines that can just grab atoms and hold on to them really tightly until we tell them to release? And if we could do that, what could we do in terms of product development? What kind of applications could we enable? And that spawned our whole mineral extraction program, where the lead candidate is lithium, but there's a lot of other metals coming up the pipe.
Yeah, like lithium right now is a really hot metal just because of the fact that the world's shifting over to renewable energy. And obviously, you need to store that energy somewhere. You have these windmills, these like hydroelectric dams, you have solar, but the sun's not shining at night or in terms of solar, for instance. So you got to store that somewhere. So lithium is a big like hot metal right now in terms of trying to extract it and then obviously create these batteries. And from what I've read, like the extraction of lithium is a very hazardous exercise. Like it's done in I think South America or somewhere like that. I've seen videos of people extracting lithium, and it's definitely not healthy in the long term. Whatever way that we could help alleviate this problem in order to get us to the renewable resource missions that we're trying to build in the future, I'm all for. So I'm really curious as to like why you guys picked lithium. Was that because you guys want to go into like the renewable energy market? What was like the genesis of that?
Yeah, I think lithium was obvious because you're right that existing lithium extraction techniques are not very environmentally friendly. But I'll tell you that's not the driving reason why we picked lithium. And the reason for that is a simple calculation. Even if lithium extraction was super environmentally unfriendly, we should still do it because the benefits of switching from burning fossil fuels to batteries is so great that the harm we do to the local environments the benefits way outweigh that cost. So it wasn't really the environmental aspect, even though our process is way more environmentally friendly, just to be clear. But that was not the driving factor. The driving factor really was this idea that one of the rate limiting steps for our ability to electrify the planet as quickly as possible and stop producing CO2 is going to be the abundance of battery grade lithium. And today we have two problems with that abundance. One, it's extremely expensive and difficult to extract lithium using traditional processes, and there's not a lot of deposits that are available for that. It takes many years to develop these deposits. And the second problem we have is that something like, and it's somewhere between 70 to 83%, the numbers keep changing depending on the year and the quarter, but a very high percentage of the world's lithium is refined in China. And so a very big problem we have today is we have a significant geopolitical competitor that has a stranglehold on the refining process. And so it doesn't matter that you can mine lithium in the United States if you have to ship all of it to China, get turned into battery grade, and then ship it back. So if we could find a way to alleviate the supply problem in a stable, robust way that can rapidly scale to the enormous demand for lithium, and if we could do so in a way that ensures the domestic production of battery grade in a way that's also much cheaper than anyone else, so we can drive the cost down over time, this is the metal that is most going to accelerate electrification of the planet. And so that's why we picked lithium as the starting point, though there's other metals that we can work on after that.
Yeah, I'd say like a lot of people would agree with you. In fact, I think you guys raised like a $49 million Series A, correct? So there's definitely in terms of the financial benefits, there's actually like people out there willing to fund you on this. Walk me through like how you were able to raise that large amount because close to 50 million for a Series A, that's a very large amount. Any tips and tricks? as to like being able to raise that amount of
There's no
material?
tips and tricks. It's just a slog until it works. I will tell you that a couple things. One of the things that I've learned in the years that I've been doing this is that people's advice is almost always highly idiosyncratic to their experiences. And so I would always take people's advice with a grain of salt, including what I'm about to say. The second thing I'll say is that the persistence is all that matters. And I know that sounds cliche, but I believe it's actually true. I think it's very hard to build a company in general, even if it's just a SaaS company or something like that. I would argue it's even harder to build a deep tech company because you have all of the commercialization problems of the first, and then you have technology that might not work, or that's going to be extremely difficult to make work and cost millions of dollars to get to work. And through all of this, things are going to take longer than you wanted to. It's going to be harder than you expect. Unexpected problems are going to occur. I don't know who said this, but there's some relatively well-known startup CEO that said that running a company sometimes is like staring in the abyss and chewing on broken glass. I forget who that quote is ascribed to, but that's very accurate. It can be real dark sometimes. I think it is more important than anything else to stay at it, keep working on it, don't give up. Because at the end of the day, it's not like the worst case scenario is you're going to die or anything. This is, you just have to keep at it as much as possible. And that's really the only piece of advice that I'd give. Everyone's going to have their own experience trying to get to where they need to go. Just don't give up.
Who was in the funding round for Series A? Can you disclose that?
Yeah, I can disclose a couple of them. There's a few large strategics I can't disclose, but the round was led by Jay Zaveri. He runs early stage investing in social capital. It's through his own fund called Natural Capital. And then we had Unless Partners join the round as well. It's a heavy industry focused fund based out of Boulder and Cambridge, Massachusetts. And we have a few strategics that we're not disclosing at this time.
And then I do have some questions regarding like the future of manufacturing. So are you guys are using like 3D printers right now to pick and place these materials, or like can you like walk me through like how you use 3D printers? Because I'm a big 3D printer guy myself. I have a ton of FDM printers as well as some
Cool.
SLA printers. So whatever it is that you're saying about 3D printers, like I actually very much do understand
No. Yeah,
that
we have quite a few printers. The printers are not used in our manufacturing process. The 3D printers are one of the products that we're working on. So we've developed an additive that you can blend with existing plastics, basically existing materials, that dramatically changes the properties of that material. For example, there's some plastics out there that are extremely difficult to 3D print. It's not impossible to 3D print. Our additive makes them 3D printable because it lowers the melting temperature, but retains the strength on the back end. We have another additive that dramatically improves Z strength. So right, when you look at 3D printing, one of the big problems with 3D printed parts is the strength in the X and the Y direction. So the direction of printing is usually reasonably good, but the strength in the Z directions layer to layer is much worse because the layers don't adhere as well together as the actual line does when you're printing it. We have an additive that basically stitches that divide and dramatically improves the Z strength, and just depends on the additive how much it improves. So we are working with a few companies, mostly in Europe, to create new blends of materials that you could fit into one of your 3D printers, and it will be easier to print and it will have dramatically better properties on the back end.
Oh, that's really interesting. Yeah, one of the biggest problems in 3D printing for me, at least, is that the shearing force where the between the layers when you're going in the Z direction always breaks off if you don't like structure it correctly. So that's really cool that you guys have this like special in-house blend that allows you to
Yeah,
increase that
and
Z.
it's literally,
Because
you could literally think of it as a stitching process. It forms these molecules that literally stitch across that divide and solve that problem.
oh, very cool. So is that like where the industry is headed towards right now, is building these like specialized molecules in order to like build larger components together? Or what are you seeing right now in the industry?
Depends on which industry. But what I'll tell you is most of the synthetic biology industry is not working in this space because the molecules we make in the 3D printing space are not made by natural proteins. There's nothing in nature that makes them, nor is there anything in synthetic chemistry that makes them. It's not really accessible to any of our competitors in this space. And what a lot of people have tried to do is make a greener version of XYZ, which is just really hard to go to market on. And you like to 3D print, you're not going to buy something that gunks up your 3D printer every third print, no matter how green it is. You want something that actually works when you want to print something. I do think that this idea of these almost self-healing materials is a long-term trend that we're seeing interest towards, that the industry is moving towards, because one, when you think about just the application of 3D printed parts, it's a huge disadvantage that there's a deficiency in the Z axis, right? That's just an enormous problem if you're thinking about any industrial applications of 3D printed parts. But even more fundamentally, plastic parts break over time. And so if you could build something where when cracks form, it stitches those cracks as they form, you're dramatically increasing the resilience of plastic components. They don't have to be thrown away as often. You can use less plastic to begin with. So I think we're seeing a lot of demand from the industry on this. And we think that's just going to continue to grow, especially as you think about the amount of manufacturing that's being built in the United States right now. There's enormous demand for high quality custom parts. And if you can replace a expensive metal part with a cheaper plastic part that has now command physical performance, yeah, there's going to be demand for that.
Yeah, so I'm curious on your take of like how you're able to scale this. For instance, in my personal experience with like 3D printers, be it FDM or SLA printers, those you can't really scale because of the fact that it's printing either like a layer at a time or maybe
Mhm.
like a bead at a time. So like you're limited on say like the speed of the head that moves back and forth, or if you're doing like SLA printers, and for the viewers, and that's basically just like resin. I'm talking about like resin printing where like there's like a light that shines onto a plate and the light is UV, and there's like an actual container filled with like UV reactive components, and that forms like a layer every time it hits it. So you're either creating it like line by line or layer by layer, but that's very slow. Like how do you scale something like this?
Yeah, so it's a great question, and it's also an important strategic component. So the 3D printing market is our starting niche market, but the real value of this additive is the self-healing property works no matter how the plastic is manufactured, right? I'm not here to profess that 3D printing is going to overtake all manufacturing methods because it isn't. The disadvantage you just talked about is the main reason why it isn't. 3D printing is useful for prototyping. No one has yet demonstrated a technology for 3D printing that can replace injection molding or anything like that, except for obviously there's exceptions for the super finely detailed parts, but that's not what the majority of plastic manufacturing is. So we're starting in 3D printing because the demand is there for rapidly prototyping new types of materials and solving this problem. And we're very happy to help that industry grow. But the materials program long term is really about, can you create these programmable materials that heal in a lot of other applications beyond 3D printing?
Yeah, I've seen a lot of cool frontier 3D printed startups that some of them do like food, like making custom made to order food. Others are more like utility, like definitely utilitarian in terms of healthcare, for instance. Like you could take a scan of a body part and you'd be able to print that in the same material, which I definitely think there's a lot of applicability in that
Yes.
market alone, just because of how unique every person is. You want to get that scan and then get that replaced with a uniquely created part like suited for you, made from the correct material. Do you guys think about expanding into like different areas, like maybe like healthcare? That'd be cool to see custom made joints in the future.
Yeah, yeah. We're certainly not going to do it because the healthcare area, our mission is to build a future of abundance for the human race. We have a lot of interesting proteins and interesting chemical reactions we've found that could be super helpful in the healthcare space in terms of creating new classes of drugs. And you're right, additives for new 3D printed parts to replace hip bones or something like that. That's not a focus area for ours because it would distract us from building a future abundance of the human race. But we're certainly at some point in the future, there might be a subsidiary or might license out some of that technology. But I think it's really, and I had to learn this the hard way, focus is an underrated quality in running a startup. And as, how should I phrase this? As important as it is that Aether as a company demonstrates the breadth of application, we are extremely careful about what new types of products we even consider because it is so easy to distract a large part of the company. And what's been interesting and what's really been a huge benefit is our mining and our materials programs have had a lot of synergy. There's some of these additives are being used in our mining program right now because they actually solve a technical problem that we had in terms of robustness of one of our systems. But that's the only reason why we're doing both of them. It's because they actually feed into each other in really interesting technical ways we didn't expect to begin with. We would never do a healthcare play right now because that would just take us so far afield from everything we're doing that it would probably kill the company, honestly.
Yeah, that'd be cool though in the future.
Yeah.
I do know that I think like Microsoft used like AI in order to scour through like mountains worth of data in order to come up with like brand new types of like chemical compounds. And there was a report that said that if they used the traditional means, it would take them like years in order to come up with a short list. And they were able to do it in I think 60 hours or something like that. where they're able to take millions of compounds, run it through their AI system, and then be able to shortlist them. And I think if I remember correctly, they were two of the compounds that they shortlisted were actually known compounds that they discovered. And so like that entire field like really impresses me of the fact that you can use AI to go and comb through mountains worth of data so that you can accelerate the material science work. Are you guys using something similar to that approach where you're using like AI or some type of advanced algorithm to comb through like mountains of data?
No, but let me clarify what I mean by that. I'm aware of the press release you're talking about. It's very PR forward. Let me put it that way. Since the company was founded, we've been convinced, and through our own experiences, that publicly available data sets for the work that we do, whether it's material science, whether it's engineering new proteins, whether it's trying to figure out new ways to mine metals, are not good enough. And they're not good enough for a few different ways. They're not big enough, they're not diverse enough. But the real problem is that there's an enormous amount of misannotation in existing data. And you don't just have to take my word at it. If you look at every similar AI problem to what we try to solve, is what a lot of drug design companies are trying to do, AI-based drug design companies, inevitably they pivot to generating their own data. Because I will tell you, we tried in the early on to take publicly available data sets and clean them up. And it is extraordinary, the amount of misannotation there. So it's great to do little proof of concepts, and it's a great way to get your feet wet and see what you can do, what you can't do. But the level of misannotation is extraordinary in some of these data sets. And it's not, there's nothing malicious behind it. It's just that there's no incentive for anyone to clean up all this data, and there's too much to clean up. And how do you know what's real or not? You can clean up, if you have text data, you can clean it up by looking at grammar rules, or we have a sense of what's correct or what's true versus what's not true. You don't have that in the chemicals world. Is this chemical reaction even possible? Yes or no? There's some basic physical laws that we can check, but once you check those off, it's really unknown unless you actually try and do it yourself. But with the data we do generate, which is these huge data sets we generate in-house through our robotics, we use some pretty large neural networks to train through it, to train off of it, predict the next round. There's basically a series of models that we use depending on the scale of the problem, but it's primarily driven by internal data sets. And then external data sets, there are some high quality ones we're aware of. They're nowhere near as big as our internal data sets, but we use them as validation sets just to make sure that there's not some confounding factor in our data that we're missing.
So how did you get these internal data? Did you partner up with somebody to get the initial like raw data
Nope.
and then build synthetic on top of it? Or what
No,
was
we have a robotic factory 300 feet that way downstairs that just generates a ton of data for us. These robots run the AI says, here's a few thousand designs I want to test that might, bind to lithium or whatever the objective we gave it was. And these robots then synthesize those protein designs, test them under multiple conditions, and feed us the data back. So it's building a robotic laboratory or factory or whatever you want to call it is possibly one of the hardest things I've ever done in my life. It is very difficult to build these things. And it's difficult not just because it's complex, there's a lot of complexity in building robotic systems, but it's difficult because it's not just about building a robotic system, it's building it so that it's stable and it produces stable, high quality data end to end in the process. That is a non trivial problem to solve, but we solved it. So, yeah, we just shorten the answer. We create our own data, we create it with our robotic laboratory, and that data is ours.
cool? And then for this robotic laboratory, did you purchase them off the shelf or did you actually
It's a
have?
hybrid.
Oh, okay.
It's
Okay.
a hybrid. You don't want to reinvent the wheel, right? If you want to get a robotic arm to pick things up and place them down, don't build your own robotic arm. That would be just I would say the stupidest thing to do. There are hundreds of vendors out there deriving from maybe a dozen or so basic designs. Sometimes, if it's available and it works well enough, yeah, buy it. Don't try and design it yourself. If it doesn't exist, you might have to design it yourself and have to build it yourself. But there's enough problems for you to solve in this space. Don't add more problems than you need to.
That's really cool. So if I was interested in this, like how would I contact you to take a look at the robotics factory or get to know more?
You can always email me at pj@aetherbio.com.
And then for someone who's interested in this area where they want to be able to take robotics and AI and be able to build like cool things, what are some like what's a good starting point in which like like a novice
Mm,
start at?
I would say so many resources right now. So first, if you're just interested in the machine learning side, the best machine learning course that I have ever seen, that's how I taught myself machine learning so many years ago, is CS, I think it's still CS 231N at Stanford. All the lectures are available online. I'm almost certain that's still the number. It's been years since I looked at it, but this is a excellent course in neural networks, how they work, how to get them to work. Now, it's not for chemistry or biology specifically, but the base, it's a incredibly solid foundation that you can build off of. And then once you have that foundation, there are now an enormous number of packages out there that can help you do machine learning for a bunch of different applications. There's one called DeepChem that's quite good, and it's gotten really good over time, open source, maintained by a lot of different people. There's a lot out there now. I would also, I think Deep Chem is another one that I would definitely work on. Yeah, I think those are the starting points. And if you go through those, you're in a really solid place to start prototyping your own data sets. If you're interested in public data sets to play around with, the NIH has a lot of data sets. Now, again, you're going to run into these annotation issues, so don't expect perfection from this. But if you just want to prototype something, the NIH has a lot of data sets that are publicly available, including, I'm pretty sure, all clinical trial results data from there as well.
Yeah, finding publicly available data that's free is really hard. Like going on like data.gov or maybe even like the Kaggle data set.
Yeah.
Those are like top of mind. I think Google has their own like data set you can search through, but a lot of the free data sets that are out there, they're not that good. Most are behind paywalls or like most are like
Right.
proprietary secret sauce that no one wants to give up. So it's I'm always curious as to where people find their data sets because other than generating your own data sets from machinery is the obvious like best case scenario.
Right.
But yeah, for a novice like starting off, like any one of those like free data set websites, Google, data.gov, NIH, Kaggle, I think those are unless
Yeah.
I'm forgetting something, those are like
Yeah,
probably
no, I think those are the big ones. And then if you're looking at the biotech side of the world, there's definitely NIH, there's NCBI, and then there's a bunch of enzymatic and protein data sets out there, and they're all open source for the most part. Things like Brenda and Keg. Yeah, you just have to deal with annotation issues.
I'm curious. You got to tell me some insider knowledge on what you guys are building. What's the secret scoop? What's the big hot stuff that you guys are working on?
There's going to be a very exciting lithium announcement later this year. It's going to be pretty amazing, the technology we're building, and it's going to be followed by a few other metals quickly after that.
Very cool. You guys partnering up with any like big brands for this?
It's a pretty big partnership coming.
Okay, I guess we'll just have to wait and see.
Yeah, it's currently confidential, but it's well in the works.
Very cool. And then what's your prediction on what's going to happen next in the field? Do you think that bigger name players are going to build their own version of what you're doing? Are they going to adopt what you're
Mm.
doing? Do you think that like 3D printing is going to go away and be replaced with something else that's more efficient and faster? What's your take on like the next big thing that's going to happen in this industry?
People are 100% going to try and copy us. That's inevitable. If we are successful, as I suspect we will be, that's just going to happen. I don't think 3D printing is going away. I just think that the market is realizing that it is primarily a prototyping tool and not a manufacturing tool. And I'm not aware of any technology out there that would solve that gap yet, which is fine. It has a very valuable role in the future of manufacturing as a prototyping tool. That's perfectly okay. But I just think that the market is resetting. There were a bunch of crazy 3D printing IPOs 2 years ago, where I think the expectation was that they were going to be the future of all manufacturing, and that just simply isn't the case for all the reasons we discussed. I do think that what I hope will happen as Aether is successful is we'll demonstrate that if you can have these programmable protein machines that can make or break chemical bonds at will with extremely high efficiency, it's not just that we can make really interesting products, but it's that we can do so in a really cost-effective way and extremely scalable way. And so really the vision for Aether over the next 5+ years is we are building our systems to exist in these modular shipping container sized units where future manufacturing plan for a next generation pharmaceutical or to extract lithium or to make a defense related material, it doesn't look like a traditional massive petrochemical plant. It looks like 3 shipping containers linked up to each other with hoses between them, and it's just humming and producing the product at the end of it. So I think that's the way to build a future of abundance for the human race. And I think that as we demonstrate that this is possible, that this is scalable, other companies will start to follow suit.
And then, so what's next for you? What's the next big hot thing that you're going to do?
I think building a future of abundance of the human race might take the rest of my natural lifespan, but if we're successful before I die, we'll have to figure out what the next big problem the human race faces at that point.
Thank you so much for being on the show. And until next time, stay curious.